Water on Mars 2021. What happened to Mars's water? It is still trapped there. New data challenges the long-held theory that all of Mars's water escaped into space. Billions of years ago, the red planet was far more blue. According to evidence still found on the surface, abundant water flowed across Mars and forming pools, lakes, and deep oceans. The question, then, is where did all that water go? The answer: nowhere. According to new research from Caltech and JPL, a significant portion of Mars's water, between 30 and 99%, is trapped within minerals in the planet's crust. The research challenges the current theory that the red planet's water escaped into space. The Caltech/JPL team found that around 4 billion years ago, Mars was home to enough water to have covered the whole planet in an ocean about 100 to 1,500 meters deep, a volume roughly equivalent to half of Earth's Atlantic Ocean. But by a billion years later, the planet was as dry as it is today. Previously, scientists seeking to explain what happened to the flowing water on Mars had suggested that it escaped into space, victim of Mars's low gravity. Though some water did indeed leave Mars this way, it now appears that such an escape cannot account for most of the water loss. Atmospheric escape doesn't fully explain the data that we have for how much water actually once existed on Mars, says Caltech PhD candidate Eva Scheller, MS-20, lead author of a paper on the research that was published by the journal Science on March 16 and presented the same day at the Lunar and Planetary Science Conference, LPSC. Scheller's co-authors are Bethany Eilman, Professor of Planetary Science and Associate Director for the Keck Institute for Space Studies, Yuk Young, Professor of Planetary Science and JPL Senior Research Scientist, Caltech graduate student Danica Adams, and Renew Hu, JPL Research Scientist. Caltech manages JPL for NASA. The team studied the quantity of water on Mars over time in all its forms, vapor, liquid, and ice, and the chemical composition of the planet's current atmosphere and crust through the analysis of meteorites, as well as using data provided by Mars rovers and orbiters, looking in particular at the ratio of deuterium to hydrogen D/H. Water is made up of hydrogen and oxygen, H2O. Not all hydrogen atoms are created equal, however. There are two stable isotopes of hydrogen. The vast majority of hydrogen atoms have just one proton within the atomic nucleus, while a tiny fraction, about 0.02%, exist as deuterium, or so-called heady hydrogen, which has a proton and a neutron in the nucleus. The lighter weight hydrogen, also known as protium, has an easier time escaping the planet's gravity into space than its heavier counterpart. Because of this, the escape of a planet's water via the upper atmosphere would leave a telltale signature on the ratio of deuterium to hydrogen in the planet's atmosphere. There would be an outsized portion of deuterium left behind. However, the loss of water solely through the atmosphere cannot explain both the observed deuterium to hydrogen signal in the Martian atmosphere and large amounts of water in the past. Instead, the study proposes that a combination of two mechanisms, the trapping of water in minerals in the planet's crust and the loss of water to the atmosphere, can explain the observed deuterium to hydrogen signal within the Martian atmosphere. When water interacts with rock, chemical weathering forms clays and other hydrous minerals that contain water as part of their mineral structure. This process occurs on Earth as well as on Mars. Because Earth is tectonically active, old crust continually melts into the mantle and forms new crust at plate boundaries, recycling water and other molecules back into the atmosphere through volcanism. Mars, however, is mostly tectonically inactive, and so the drying of the surface, once it occurs, is permanent. Atmospheric escape clearly had a role in water loss, but findings from the last decade of Mars missions have pointed to the fact that there was this huge reservoir of ancient hydrated minerals whose formation certainly decreased water availability over time, says Eilman. All of this water was sequestered fairly early on and then never cycled back out, Scheller says. The research, which relied on data from meteorites, telescopes, satellite observations, and samples analyzed by rovers on Mars, illustrates the importance of having multiple ways of probing the red planet, she says. Eilman, Hu, and Young previously collaborated on research that seeks to understand the habitability of Mars. Thank you for watching.